KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
See here, ma. In this class, we are going to start new chapter, Thermodynamics. So this is the first class in this chapter, Thermodynamics. Our previous chapter was thermal properties of matter. There we had a discussion about heat, temperature, measurement of temperature and thermal expansion of matter, etc. Right. But now why I am saying about the previous chapter means the things two majorly, one is heat, another one is temperature, we have to take into this chapter also. We have to take to consider, we need to consider into this chapter also, because as I already told you what is heat and what is temperature. See, why we need to consider means this chapter is also talking about, right? This chapter thermodynamics means actually basically which is a branch of physics. Thermodynamics is a branch of physics, deals with the concept of heat and temperature and the interconversion of heat and other forms of energy. I will repeat once again. Thermodynamics is the branch of physics that deals with the concept of heat and temperature and the interconversion of heat and other forms of energy. Interconversion of heat and other forms of energy. Okay, right. So you please be concentrate. In this class we are going to concentrate towards the introduction to thermodynamics, and afterwards we are going to discuss thermal equilibrium. Thermal equilibrium, right? That is. After completion of this, we will go to the next continuation topic in our next upcoming classes, right? First, see what is the information we can discuss from the introduction of thermodynamics, right? See, as I already told you in our previous chapter, we studied thermal properties of matter, okay? But in this chapter, we are going to study the laws that govern thermal energy. See, the laws which governs the thermal energy are heat energy, and we will also study the processes where work converted into heat and vice versa. And we will also study the processes where work converted into heat and vice versa, and heat into work also. For example, if you see the winter, sometimes if when the temperature is too cool, when you come out from the house, see, generally we are going to rub our palms together. Then we will feel warmer, right? And that hands we are going to keep on our face sometimes, okay? See here, whatever the work done due to the rubbing of hands produces heat. Am I right? Similarly, opposite to this, if you take steam engine, that steam engine converts heat of the steam used to convert into work. So that work helps for the steam engine for the moving of pistons which in turn rotate the wheels of the train. So once upon a time, right? So we used steam engine for the trains. So there what's happening means we are using steam, that is what heat energy, will be converted into the work. See, that work will run the pistons, will move the pistons. These moving pistons will will rotate the wheels of the train so that the train is going to move. Okay, ma? That is. Next, see here, generally in physics, we need to define the notions of heat, temperature, work, etc. Work, etc. more carefully. Okay. But historically, it took a long time to arrive at the proper concept of heat. Historically, it took a long time to arrive at the proper concept of heat. Before the modern picture, heat was regarded as a fine visible fluid filling in the pores of a substance. Before the modern picture, what we had in these modern days, heat was regarded as a fine invisible fluid, right? Fine invisible fluid filling in the pores of a substance. Filling in the pores of a substance. Okay, that's what I mean. Before this before coming to this modern picture of heat, it was regarded as a fine invisible fluid filling in the pores of a substance. Filling in the pores of a substance. Okay, right. See, on contact between heat body and a cold body, the fluid flowed from the colder to the hotter body. Is it correct? Shall I say like this? Shall I say like this? Because see, I will repeat once again. On contact between a hot body and a cold body, the fluid that you can call it as caloric flowed from the colder to the hotter body. Just keep in mind that, then I will come to the conclusion. This is similar to what happens when a horizontal pipe connects to two tanks containing water up to two different heights. See, the flow continues until the level of the water in the two tanks are the same. Likewise, see, just now what I told you, that is what caloric. In case of caloric picture of heat flows until the caloric levels, that is the temperature equalize. Okay, right. And I already told you in our previous classes, in our previous chapter, right, in our previous classes, I told you heat always flows from a body at high temperature to the body at low temperature. Okay, right. Now, see, the picture of heat as a fluid was discarded in favor of the modern concept of heat as a form of energy. See, in modern concept, what we are saying, heat as a form of energy. Heat as a form of energy, right? See, an important experiment in this connection was due to the Benjamin Thomson, also known as Rumford, right? Count Rumford in 1798. See, he observed that boring of a brass cannon generated a lot of heat. Boring of a brass cannon generated a lot of heat, indeed enough to boil water. See, generally to boil water, how much heat energy we require? The temperature of the boiling water is 100 degrees centigrade. That's okay. See, where the water is converting into steam. Right, before that also, based on the surroundings temperature, the water is going to boil. That will be different. But here what he is saying is, according to Benjamin Thomson, observed that boring of a brass cannon generated a lot of heat, indeed enough to boil water, right? More significantly, the amount of heat produced depend upon the work done. The amount of heat produced depends upon the work done. Okay, right. See, for example, if you see horses which we were used for turning the drill in olden days, right? See, whatever it may be, here the important statement is the amount of heat produced depends upon the work done, but not on the sharpness of the drill. See, this is the important point. So he has given both the depending point and independent point. So the depending point is the amount of heat produced depends on the how much amount of work we did, not on the sharpness of the drill, right? In caloric picture, a sharper drill would scoop out more heat fluid from the pores, but this was not observed, right? This was not observed. So like failure of the failure step. Next, see, a most natural explanation of the observations was that heat was a form of energy, and the experiment demonstrated conservation of energy from one form to another, that is from work to heat, okay, right. Now next one, see here, thermodynamics is a branch of physics that deals with the concept of heat and temperature, and the interconversion of heat and other forms of energy, okay, that is, you can also say that thermodynamics is a macroscopic science. It deals with the bulk systems and does not go into the molecular constitution of matter. It does not go into the molecular constitution of matter. In fact, its concepts and laws were formulated in the 19th century before the molecular picture of matter was strongly established, right? Thermodynamic description involves relatively few macroscopic variables of the systems, which are suggested by common sense and can be usually measured directly. See, suppose in case of microscopic description, a microscopic description of gas, for example, would involve specifying the coordinates and velocities of the huge number of molecules which constitute the gas, right? See, the description in kinetic theory of gases is not so detailed, but it does involve molecular distribution of velocities. And regarding the thermodynamic description of gas, you can say, on the other hand, avoids the molecular description altogether. Instead, the state of a gas in thermodynamics is specified by macroscopic variables, right? See, macroscopic variables such as pressure, volume, temperature, mass and composition that are felt by our sense perceptions and measurable, okay, right? See, there is somewhat sometimes we thought that the thermodynamics and mechanics are relevant. Yes, relevant in one aspect, but not in all the aspect. See, what is the difference you can say means here in mechanics generally, right? I'll come to this point conclusion, but before that you listen something. See, the distinction between mechanics and thermodynamics is worth bearing in mind. See, in mechanics our interest is in the motion of particles or bodies under the action of forces and torques. Thermodynamics is not concerned with the motion of the system as a whole. Right? It is concerned with the internal macroscopic state of the body. Suppose, for example, if you come to the point of example to understand deeply, see, for example, if you fire a bullet from a gun, what changes is the mechanical state of the bullet is, for example, generally kinetic energy, not its temperature. Otherwise, if the same bullet pierces in the wood, it stops. See, the kinetic energy of the bullet get converted into heat. See, changing the temperature of the bullet and the surrounding layers of wood. See, temperature is related to the energy of the internal. And motion of the bullet, not to the motion of the bullet as a whole. Okay, see here what he is saying is, when a bullet comes out from the gun, It's moving from one place to another place, but when it pierces into the wood, see, it causes to create somewhat heat, right? That heat may increase the heat of that particular piece and as well as bullet also. See, what he is saying is, before entering into the wood, it is like a kinetic energy and you can treat it as mechanical, but when it enters into the wood, we have to take it into the part of like dynamics to discuss the situation what is present there. That's what he is explaining. Right, next one, next important definition in this chapter, thermal equilibrium. Thermal equilibrium, right? See, generally what is meant by equilibrium? In our mechanics we came to know what is meant by equilibrium. Actually, equilibrium means in mechanics, it means that the net external force and torque on a system are zero, right? So in mechanics, generally equilibrium means the net external force and torque on a system are zero, right? See, the term equilibrium in thermodynamics appears in a different context. The term equilibrium in thermodynamics appears in a different context, right? Generally we say that the state of a system is an equilibrium state. The state of a system is an equilibrium state if the macroscopic variables that characterize the system do not change in time. That characterize the system do not change in time. For example, a gas inside a closed rigid container completely insulated from its surroundings with fixed values of pressure, volume, temperature, mass and composition that do not change with time is in a state of thermodynamic equilibrium. Right. See, whatever I told that I am going to concise now. See here, the state of a system is in equilibrium state if the macroscopic variables that characterize the system like pressure, volume, temperature, mass and composition of the gas that do not change with time. Composition means composition of the gas that do not change with the time, right? That's what we can say the meaning of thermodynamic equilibrium. Thermodynamic equilibrium, right? Okay. See, now we are going to discuss what is meant by adiabatic wall and what is meant by diathermic wall, right? Adiabatic wall means is an insulating wall that does not allow flow of energy from one to another. But it can be movable from one place to another place. It can be movable, but it does not allow flow of energy from one to another. Right? Next, diathermic wall. Diathermic wall means a conducting wall that allows energy flow. A conducting wall that allows energy flow from one to another. A conducting wall that allows energy flow from one to another, right? That is next. See, this is about adiabatic wall and diathermic wall. Adiabatic wall and diathermic wall. Okay, right. See here. Now we are going to see, right? Now we are going to discuss these two things. See, after completion of this adiabatic wall and diathermic wall, right? Adiabatic wall and diathermic wall. Now we are going to discuss one example to understand thermal equilibrium in detail. Okay, see here. In general, whether or not a system in a state of equilibrium depends on the surroundings and the nature of the wall that separates the system from the surroundings. Am I right? I will repeat once again because it is very important point. In general, whether or not a system is in a state of equilibrium depends on the surroundings and the nature of the wall that separates the system from the surroundings. That is one thing, right? See, now based on this we are going to discuss one example. You just consider two gases, capital A and capital B, occupying two different containers, right? Okay, now we know experimentally that pressure and volume of a given mass of gas can be chosen. We know experimentally that pressure and volume of a given mass of gas can be chosen to be its two independent variables. Right? We know experimentally that pressure and volume of a given mass of gas can be chosen to be It's two independent variables, right? See, for example, initially you assume like pressure and volume of the gas like PA and VA, right? Afterwards you can take it as PB and VB, because for A, PA, VA, for B, PB, VB respectively, right? Suppose initially that the two systems are put proximity but are separated by an adiabatic wall. Separated by an adiabatic wall. See, what is adiabatic wall? I already told you. Suppose if the two systems are going to separate by adiabatic wall, then what will happen? The two systems, you can say that, are insulated from the rest of the surroundings. The two systems are insulated from the rest of the surroundings also by similar adiabatic walls. Also by similar adiabatic walls, right ma? That is, suppose it is found that, so in this case it is found that any possible pair of values PAVA will be in equilibrium with any possible pair of values PBVB, because adiabatic wall means, which is what, a wall that does not allow flow of energy from one to other, right? Next, first we separated two containers, that is what, which consist gas A and which consist gas B, separated by adiabatic wall. Now we are going to separate by diathermic wall. Diathermic wall means what? A conducting wall that allows energy flow from one to another. So in this case, it is then found that the macroscopic variables of the systems A and B change spontaneously until both the systems attain equilibrium states. Until both the systems attain equilibrium states. Right? Okay. Now, after that, there is no change in their states. After that, there is no change in their states. See, the situation in this case, that is what, the pressure and volume variables of the two gases change to PB dash, VB dash and PA dash, VA dash, such that the new states of A and B are in equilibrium with each other, right? So what can we say here? What is the conclusion you can give based on this example and based on this the two containers having gas A and gas B separated by initially adiabatic wall and then diathermic wall? Based on this, what is the conclusion you can give? Right? See this. See, there is no more energy flow from one other in case of diathermic wall. When there is no more energy flow from one to another, you can say that the system A is in thermal equilibrium with the system B, right? See, first container A, container which consists of gas A and container which consists of gas B separated by adiabatic wall. There is no situation, there is no talking about thermal equilibrium. But when those two are separated by diathermic wall, right, there is a discussion about thermal equilibrium. So the pressure and volume variables of the two gases will change to PB dash, VB dash and PA dash, V dash, PA dash and VA dash. Okay, right. So at the time, because of these two gases, you can say that the system A is in thermal equilibrium with the system B. Okay, right. See, you just think of it. I'm going to put some questions in front of you. See, what characterizes the situation of thermal equilibrium between two systems? You can guess the answer. So you just think, then you will get the answer based on the discussion what we had in this class. That is what, introduction to thermodynamics, and after that we came to discuss thermal equilibrium. Right? That's what you can say. Generally in thermal equilibrium, the temperatures of the two systems are equal, right? Temperature of the two systems are equal. So if the two systems are having the same temperature, if the two systems which are connected to each other otherwise are having same temperature, means then those two systems, you can say that which are in thermal equilibrium, right? So in this discussion, see, while discussing the importance of thermal equilibrium, we are going to get another important law in thermodynamics, that is zeroth law of thermodynamics. Okay, right. That we will discuss in the next class, right? So in the next class we will continue with the zeroth law of thermodynamics, and then what is heat, what is internal energy and work. Okay, and after completion of that we will continue with the first law of thermodynamics if possible, right? Thank you.